Okay, so this is our review video for test number 3. So we said it was partial fractions and logarithms and exponents. So let's just look at a couple of problems that are similar to what you should see on the test. So let's look at partial fractions first. So let's say we have this rational expression, and so I'll give you one where you can factor the denominator. Hopefully you can do it without using the quadratic formula. So the first thing you do is you factor the denominator. So in this case you get x plus 4 and x plus 1. And the whole idea for partial fractions is to take a rational expression with a factored denominator and make it into two separate rational terms that are the factors of the denominator. So since I can factor this into x plus 4 and x plus 1, these are the two denominators. And I'm just going to give you one. If I give you one, it'll be where you just have two linear factors. So as a consequence, you should be able to use the shortcut approach here to combining these two. So what you do is you cross multiply. So you have a times x plus 1 plus b times x plus 4, and then you multiply the denominators together, and you see that process ends up with the same denominator. So then you can then say, okay, well, if they have the same denominator and they're equal, they have to have the same numerator. And then you strategically pick the value of x to evaluate this function at. Well, I'm going to choose -1 because that'll make this term go to 0. And I'll choose -4, which will make that term go to 0. And then you plug that into the equation that we have. So you'll have 7 times -1 plus 4 is equal to, so here we'll have a times 0, because you'll have -1 plus 1. So that one goes to 0. And then you have the second term, which is b times x. B times -1, x is -1 plus 4. So on the right-hand side we have 3, and on the left-hand side we have 3, -3. So we got -7 plus 4 is -3. And here we have b times -1 plus 4, which is +3. So you get b is equal to -1. -3 divided by 3 is -1. And you do the same thing over here. Pick 4. So you plug 4 to the left-hand side, and you plug 4 into the right-hand side. In this case, this term does not go to 0, so you'll have 4 plus 1, but the second term in the parentheses does go to 0. So when you plug 4 into x plus 4, if you plug in -4, you get 0. So that term cancels out just like that one. So on the left-hand side, you'll have 28 plus 4, which is 32, and then we'll have 4 plus 1, which is 5, so you get 5a, and therefore a is equal to 32 over 5. And so the final answer I'm looking for is now plugging these in. So you'll have 32, a is 32 fifths, so put 32 in the numerator, put the 5 in the denominator, and we'll multiply it by x plus 4, and then you have plus b, which is -1, so we have -1 divided by x plus 1. And you can check this by just going through the math again. So if you have 32 times x plus 1, cross multiplying here, -5 times x plus 4, and yeah, something doesn't look right, does it? So what did I do wrong? I'm just looking at it. I get 32x minus 5, which is not, it's not 7. So obviously I've done something wrong. So again, I'm not going to edit this out because it just shows you how checking your answer sometimes important. So let's go back to the beginning and see if I can, maybe you've already figured it out. So let's see. Okay, it's not jumping out at me, so yes, I am going to pause the video. So hold on. Okay, yeah, I see where it is. I plugged in +4 here, and I shouldn't put in +4. I should put -4. So let's start over again. Well, we don't have to go all the way back to the beginning. So you're going to have 7 times -4, and you're going to have -4 plus 1. Okay, so 7 times -4, that's -28, plus 4 is -24, and then you'll have a times -3, or you get a is equal to -24 divided by -3, which would be 8. Okay, so let's plug that back in here now again. So we got 8 divided by x plus 4 minus 1 over x plus 1. So again, cross multiply, you'll have 8 times x plus 1 minus 1 times x plus 4, all divided by x plus 4, x plus 1. And if we multiply out the numerator, you're going to have 8x plus 8 minus x minus 4. So this is a 4. So you get -x, -4. That's all divided by x plus 4 times x minus 1. And 8 minus 1 is 7. So you get 7x, and 8 minus 4 is 4. And there we go. So that is the right answer. So yeah, be careful when you're working these things out. So that's partial fractions with 2 linear terms. So just know how to do that. Okay, I could fake you out here and do the ones with 1 linear term, 1 quadratic term, but if you need partial fractions and you take calculus, they're probably going to teach you this again. So you got practice doing it in homework problems, so I'm not going to belabor that. Okay, moving on to chapter 3. So the first thing we're going to talk about is exponential functions and their graphs. So you need to be able to plot them and transform them. So, let's say I give you the function f of x equals 3 to the x. And I ask you to plot that function. And I ask you to do it with at least so many data points. Usually you can do at least, definitely could do 3, usually 4, maybe 5, depending upon what the base is. So I want you, when I ask you to do this, I want you to put together a table. And I think in this case 4 is probably going to be as many as we can get that make much sense. So you're going to have a column here which is x and a column which is 3 to the x. And remember, what we do is we're going to pick values of x that are -1, 0, +1, and 2. And so when you evaluate this, you get 3 to the -1, which is 1/3. And then you get 3 to the 0, which is 1. Any number to the 0 power is 1. Then you get 3 to the first power, which is just the number. And then you get 3 to the second power, which is 3 squared, which is 3 times 3, which is 9. So let's plot those 4 points. So you got -1, 1/3, so it's going to be really close. And then this big, that's the important one there, where you go through the y-axis. Then you go 1, 3, 1x up 3y, 2, 9. And so then you would draw your, make sure your curve, this line is really close to the x-axis. Sometimes it's hard to draw it without crossing it, but I'm not going to take off if you cross it just a little bit, but you got to be pretty close to the x-axis. Okay, so that's the function. Now, beyond that, I may ask you to do something that involves some kind of transformation. So, let's use the same base, but I may give you one where you have to plot it with one base and another one where you have to do a transformation. So let's look at just a couple of examples of things you might see. So you could have something like this. So this is the y shift. So I'm going to draw it in and I'm going to erase it just to show you how you do it. So in all of these cases, drawing the parent function is probably important. And then all you have to do is kind of shift everything. So if you have these 4 points, you could just shift them and then redraw the curve. So what we have here is 2 vertical units. So you just move every point. So instead of 1, I'm at 1 plus 2, which is 3. Instead of 3, I'm at 3 plus 2, which is 5. And then instead of at 9, I'm at 11, which would be up here. And then instead of at 1/3, I'm going to be 2 and 1/3. And also the asymptote changes. So in this case, instead of approaching 0, I'm going to approach y equals 2. Now I shouldn't have these crossover. It's just because I'm doing a sketch. Okay, so that's that first one. Okay, let's do the next one. Look at all the different possibilities. So then you could also have, let's just put a negative sign out in front like that. And really the best thing to do is to do the reflections first and then do the translation. So what we would do first, sort of, the first step would be, instead of doing 3 to the x, would be -3 to the x. And this is negative out in front of this is an x-axis reflection. So if I did that, everything that's on this side goes to that side. So you can kind of mirror it. Instead of up 1, you go down 1. Over here, instead of up 3, you go down 3. And instead of going up 9, you go down 9. And here, instead of going up 1/3, you go down 1/3. And then instead of approaching the x-axis from the top, you're going to approach it from the bottom, like that. And if you do these intermediate steps, do it really lightly. Use like a dashed line or something. Okay, and then the next thing you do is you add 2. So adding 2 is going to shift it up. So instead of going from 1 to 3, we're going to go from -1 to 1. Instead of going, this is 1, -3, so we're going to go up 2. So go 1, 2, so that point there. Here we're in -9, so we're going to be -7. Here we were -1/3, so we're going to be right here. And again, you want to shift your asymptote here, so you have some reference point to draw this. So then you'd have this arrangement. So that's I could say this is f of x equals 3 to the x, and I could call the green one g of x is equal to -3 to the x plus 2. So we've done translations in the y direction, and we've done reflections across the x axis. So I'm going to again erase all this stuff till I'm back to my parent function. Okay, let's go back here, and we will do a x-axis reflection. So, I mean a y-axis reflection. So if you have 3 to the negative x plus 3, and you know, listen up here, because this is where you guys messed up this previous time. I want you to do it again. I'm not going to be as forgiving as I was last time, even though I'm not sure if I was that forgiving. So you factor out the negative sign. So you're going to have negative times the quantity x minus 3. So instead of negative x plus 3, it's negative the quantity x plus minus 3. So what I have here is I have a y-axis reflection and plus 3x shift, because this is negative x minus h, so h is positive 3. So again, what I would do is instead of doing a y-axis reflection, an x-axis reflection, I'd do a y-axis. So here's the y-axis, so I want to reflect it. So this point is on the y-axis, so it stays where it is. This point goes over here. This point goes over there. So instead of going plus 2 plus 9, I go minus 2 plus 9. Here, this one here goes over to there. The horizontal asymptote stays the same, so because I didn't have any y shift. And then you go down like that, and there you go. Okay, so that's the y-axis reflection. And then you move the shift in the x direction 3 units. So what I do is I have these 4 points. So let me move this 1, 2, 3, 4. So that goes to there. Here we down here 1, 2, 3, 4. All you're doing is counting. This one 1, 2, 3, 4, and this one here, which is 1 1/3, would go 1, 2, 3, 4. We go right there, and so then you could sketch it in. And again, the horizontal asymptote doesn't change. The only time the horizontal asymptote changes is if you have a y shift. So that's this green is that function. And they only get, so yeah, I've done both the y-axis reflection and the x shift. So we've covered everything there. So let's talk about logarithmic functions. Same kind of deal, except it's opposite, right? They're inverse functions of each other. So over here, you notice I had negative 1, 0, 1, 2. Over here, we'll kind of go the other way. So I'm going to use a base of, let's use a base of e, just for the heck of it. So what I'm looking at, the equation is f of x equals log base e of x. That's my parent function. Now you could also write this as the natural log of x. So what we're going to have here is we're going to have a log base e of x. So what you want is negative 1, 0, 1, 2. So how do you go in the opposite direction? Well, if we go back to this was if we went this way, we took the base and raised it to this power. So we're going to do this opposite thing here. So you take the base, which is e, and you raise it to this power. You take the base, which is e, and raise it to this power. You take e, which is the base, raise it to this power, and so forth. Now, this e to the 0 is e to the 0 is 1. Sorry. So anything raised to the 0 power is 1. E to the first power is e, which is 2.7. I'll just round it off to 2.7 because we're not going to be able to draw any more accurately than that. And if you do 2.7 squared, 2.7 squared is 7.3, so that's close enough. Here I have 1 over e, so I have 1 divided by 2.7, and I'll get 0.37, 0.37. Okay, so this is x. So it's better to go this way because we need the same kind of points. So you'll notice that x is never negative. So what we have is, here's x, and we'll go from, from negative 10 to positive 10. So we have x is about a third, y is negative 1. About there. X is 1, y is 0. It's this one. X is 2.7, so you go 1, 2, 2.7, and that gives you 1. And then you have 7.3, 1, 2, 3, 4, 5, 6, 7.3, that's 2. You see with those, and with this vertical asymptote at 0, you can use that as a guide. And so that gives you a pretty good curve. This thing's going to, again, approach the y-axis, but it's never going to cross it. So that's my parent function. So from that, you can do these transformations. So let's look at the transformations again. So, log base e of x minus 3. So if you've got your parent function, all you have to do is move everything down 3 units. So 1, 2, 3, that goes right there. This one here goes 1, 2, 3. Here's this one, 7.23, 1, 2, 3. And this one is at negative 1, so we go 1, 2, 3, goes like that. And this horizontal asymptote, well, the vertical asymptote doesn't change, so it's going to be, this blue curve is going to be slightly to the right of the red curve, but it's going to be hard to draw that. Okay, so that's how you do a vertical. Let's take all those points out there. We'll leave the parent function up there. Okay, so the next thing is let's put a negative sign in front, log base e of x, and I'm going to plus 2. That's inside the parentheses. So what we have is we have two things. We have an x-axis reflection, and we have a minus 2x shift, x minus h. Okay, so we've already drawn the parent function. So what I said was you should always do the reflection first. So this is a reflection across the x-axis. So this point stays the same. This one goes up to positive 1 from negative 1. This goes from positive 1 to negative 1. This one goes from positive 2 to negative 2. Same. So that's, again, you can draw that in very lightly. So that's the reflection. And then you can do the shift. So you're going to shift them 2 in the negative direction. So we have these 4 points. 1, 2, move that. This one, so you get 1, 2 is right there. Here's this one. You go 1, 2, which puts you about here. And then this one, 7.2, 7.3 goes 1, 2 units. And the vertical asymptote shifts, so you want to move that. When you move in the x direction, you want to shift the vertical asymptote so that you can use that as a guide to sketch this thing in. So that's what that involves. Okay, the last thing we're going to do is we're going to have a let's do both of them. So we're going to have a negative log base e of negative x plus or minus 2. And that's all in parentheses. So you got to be careful. It's got to be in parentheses or you're not going to see it correctly. And I forgot to erase this stuff, so let me go ahead and erase everything except the parent function, which is the red curve. Okay, so there's the parent function. So, what I'm going to have here is I'm going to have an x-axis reflection. That's due to the negative sign out in front. I'm going to have a y-axis reflection inside. Pay attention. Factor out that negative sign inside. So you'll have negative the quantity x plus 2. So the negative out of both of them give me two positive quantities. And that means my x-axis shift is going to be minus 2, because this is x plus 2. So we just did the, here's the x-axis reflection. So let's do that first. You could do either one first. Now, if you reflect it across the y-axis, now what's going to happen is this thing's going to now look like this. And I'm being a little loose with the point, so let's not be too crazy here. So this across the x-axis, this point stays the same because it's on the x-axis. This one's going to go up to here, which is plus 1/3, or plus 1.3, whatever the reciprocal of e is. And then you go plus e, so that's 1, 2, 2.7, down 1. And then 7.3, which is 7.3, which is about there, and you go down 2. So, and then when you do the y-axis reflection, now I'm looking at the green points. So this point goes over here. This 1/3 goes to right there. Or no, approximately 1/3. This one goes from 2.7 to negative 2.7, which is right there. So this one goes over there, and this one goes down to negative 7.3, which is about right here. Okay, so that's both the x-axis and y-axis reflection. And then the last thing is you shift 2 units in the x direction. So we're going to move this to there. So that goes 2, 1, 2. This one goes 1, 2. This one goes 1, 2. This one goes 1, 2. The vertical asymptote shifts, so we have something to draw this more accurate, and then we draw through the 4 points and then approach the vertical asymptote. Okay. So that's how you do all those transformations. Then there are at least 5 problems with that transformation on there. But I do want you to make up the tables. I'll leave you enough space to generate these tables. I don't just want you to do a inaccurate thing. Okay, the next thing is to write logarithmic expressions in exponential form and exponentials in logarithmic form. So let's say we have that 4 to the second power is 16. So that's the exponential form. So what you want to do when you go to logarithmic form is this becomes the base of the log. So if I do log, this 4 comes down there. Okay, so the base of the exponent becomes the base of the log. Then you have this number right there. That becomes that number. And finally, the exponent is that thing. So this exponent thing comes down like that. And remember, the way the logs work is, what number do I need to raise 4 to get 16? What do I need to raise 4 to get 16? The answer is 2, and you can see 4 to the second power is 16. So if you want to draw, something that makes you understand this base becomes the base of the logarithm. The exponent becomes the answer. The answer becomes the argument of the logarithm. And you can go the other way. Let's say log base 3 of 27 equals 3. Okay. So again, this is the base, right? So that's going to be the base of the exponent. So let's just draw a little dashed line around here, draw an arrow, so that goes there. The answer here is going to be the exponent over here, and the right-hand side is the argument of the logarithm. It's saying, what power do I need to raise 3 to get 27? Well, 3 to the third power equals 27. So you got how many of those? At least 3 or 4 going one way or the other, converting exponential to logarithmic and logarithmic to exponential. The key thing again is that the base of the logarithm is the base of the exponent. The base of the exponent is the base of the logarithm. And these other things switch sides. Okay. The next thing is to look at combining and separating logarithmic expressions using the properties of logarithms. So let's say I have the natural log of x cubed y divided by z squared. So this is, it's not exactly, it's not this one. The logarithm of a times b is the natural log of a plus the natural log of b. That's one of the properties. The other one is the natural log of a divided by b is equal to the natural log of a minus the natural log of b. So that's the quotient version. Another way to think about this is, anything that's in the numerator has a positive sign in front of it when you separate it. And you keep the exponents until you've separated them. So the x cube's in the numerator, so put that with a plus. Y is in the numerator, so leave that as a plus. Z squared is in the denominator. So we use both of these rules to break that up. And then finally you want to take the exponents out. So here we have an exponent of 3, so that becomes that. This one doesn't have an exponent, so that just stays the same. And we have an exponent of 2, so we bring that out. So that's what I'm looking for when it says expand. So this is the process of expansion. Let's do one more here. So let's say I have log base 2 of x minus 1 squared times square root of y divided by, well, let's do the square root of z, so you don't think y always has to be in the numerator. Square root of z divided by y. Let's do the cube root of y. So the first thing, just like over here, you want to separate these things. So the ones that are in the numerator are going to be positive, and the ones that are going to be in the denominator are negative. So I don't know why I did that. So you got to subtract one more item. So you're going to subtract log base 2 of the cube root of y. Okay. The next thing we're going to do is we're going to change these square roots and cube roots into fractional exponents. So the square root is to the 1/2 power, and the cube root is to the 1/3 power. And the fourth root would be the 4th power, 1/4 power. So you get y to the 1/3 power. Now we've got numerical exponents. We can pull those out. And once you've gotten the exponents out and you've separated everything out, then you're done. Okay, so those are examples of expanding. Okay. Okay, the next thing is to go the other direction. So let's say we have the natural log of 2 times the natural log of x plus 1/3 times the natural log of y minus 3 times the natural log of z. So if you kind of look at what we did here, we go the opposite way. So, you know, we've got everything out. So the first step is to put the exponents in. Because the only time that you can combine these logarithms is when they don't have any, all they have is plus or minuses, but there's no constant up front. So we couldn't combine them at this point. We have to move any numbers that we have as a multiplier inside as the exponent. Then you can combine. So here what we did was we changed square roots into half power. So we could do the same thing here. We could say, you know, we have the natural log of x squared plus the natural log of the cube root of y minus the natural log of z cubed. Okay. And then we can combine them into a single logarithm, and everything that has a plus goes in the numerator, and anything that has a minus goes in the denominator. Okay, so that's one example. You can look at your homework for more examples. One point is, if you had the natural log of x squared minus 2, this is not multiplied or divided, and basically you can't do anything with that. I mean, that's the final form. You cannot take the 2 out. This does not equal 2 times the natural log of x minus 2. Whatever you do to this stuff, you have to do to both of them. So, you know, if I had, let's see, I had the natural log of, you know, x squared minus 2 squared, then you, because this square is applied to the whole thing, it would be 2 times the natural log of x squared minus 2. So it has, this exponent that I pull out has to apply to the whole thing. Here's one I just thought of, might be interesting. Let's see, you had the natural log of x squared plus 4x plus 4. You know, I can't do anything with that. But if I factored this, you'll see it's x plus 2 squared. So this can be factored as x plus 2 times x plus 2. And now that you have the square out front, you could say this is 2 times the natural log of x plus 2. Okay, that's kind of a special case. That's usually when they're trying to trick you into trying to solve the problem. If I ever ask you to take the logarithm of a negative number, you say does not exist. So you could try plugging that in your calculator and you'd find out that you get it. It would say error. So you know, just pay attention to that. If you see a problem where there's a negative argument, then you can't do anything. You just stop and say, I can't do anything because it's negative. Okay, now we're going to look into solving logarithmic expressions, so that an exponential expression. So we'll do a real simple one. I've got a couple of simple ones on there. You know, if you have 3 to the x equals 71.5. So in this case, I don't have any constant out here multiplying the exponential term, so I don't have to go any further. I just need to take the natural log of both sides. Remember, if it's an exponential equation and I'm solving for x, I can use any base, so it's easiest to use the natural log because that's on your calculator. Now, by taking the natural log of this exponent, I can bring out the variable. Instead of being the exponent, now it's not exponent anymore. And so x in this case is going to be the natural log of 71.5 divided by the natural log of 3, and I don't want you to leave it. I want you to give me an answer. Whatever that is, plug it into your calculator. Natural log of 71.5 divided by the natural log of 3. It's 3.886. Now remember, don't do this. Natural log of 71.5 divided by 3. So when you do this division, you're not combining the logarithms together. They're still separate. So don't do that. Okay. Okay, so that's one thing. You could have it part of a bigger expression. Let's say we put some exponent in here like that, and we multiply it by some constant, and then we have some arithmetic over here like that. Okay, so we got a lot of things going on. We need to get to this point, so we just need to do the algebra to get to that point. So in this case, I would first subtract 5 from 97, which is 92. Then I would divide both sides by 4. 92 divided by 4 is equal to 23. And now I'm back to this problem. So you get 3 to the x plus 2 equals 23. Now, again, you can use the natural log. Natural log of 3 to the x plus 2 equals the natural log of 23. Take the exponent out. That makes it so that it becomes an algebraic expression. Divide both sides by the natural log of 3. So I'm going to go ahead and calculate that. So natural log of 23 divided by the natural log of 3 is 2.85. And then subtract 2, you'll get 0.85. Okay, so that's pretty much it. Just, a lot of different varieties of it. There's 1, 2, 2 or 3 of those. And then you have the other direction. So let's say we have log base 3 of x equals 4. Solve for x. Well, when you're solving a logarithmic expression, you have to have this base match up. So this is not an option. So you're going to have the base 3 on both sides. So we take that number. If you want to draw a little arrow and remind you. And then you have log base 3 of x and 4. So we have log base 3 of x equals 4. So 3 to the log base 3 of x equals 3 to the 4. And because these bases are the same, then you can say the inverse properties of the logarithm and the exponential mean the answer is x. And so the answer in this case is 81. Log base 3 of 81 is 4. What do I need to raise 3 to get 4? What do I need to raise 3 to get 81? The answer is 4. Okay, so that's kind of the simplest scenario. Let's just make another example. So let's say we have log base 4. So 3 times log base 4 of x plus 1 equals 4. Okay, so I'm trying to solve for x. I need to get to this point. I need to have no coefficient in front of this. The argument I'm not worried about. That's going to come out ultimately. The first requirement is that I get rid of anything that I combine any like terms and I I get the coefficient of 1 in front of this. So what I'll do is I'll divide both sides by 3, so I'll get 4/3 on my right hand side. So 4 divided by 3 is 1.3333333. Okay, so notice one coefficient of 1 in front of it. Now I look at the base here. It's a base of 4, so that means the base of the exponent has to be 4 that I'm going to use to solve this, to rewrite this logarithmic expression as an algebraic expression. So I'm going to take log base 4 to the log base 4 of x plus 1 and 4 to the 1.33 power. But 4 to the log base 4 of something is just the argument, which is x plus 1, and 4 to the 1.33 power is 6.35 approximately, and subtract 1 from both sides, you get 5.35. Okay, so those are the kind of things. You know, if this equation was originally, you know, where I had the 4 was on the left-hand side, the first thing I'm going to do is I need to get this term by itself. So all of the constant stuff goes to the other side, is combined. Then I need to, once I've gotten the logarithm term plus the coefficient and everything else to the other side, then I can divide by the constant so that I get a coefficient of 1. At that point, you see what the base of the logarithm is. That's the base of your exponent. Okay. Now it'll be one of those where, let's say we have the logarithm of x plus 1 minus the logarithm of x minus 2. And hopefully this has a solution. I'm going to say it's 7. I'm just making these up, so we'll see if it works or not. So when you have one of these cases where you have two logarithm terms, you want to combine them using the properties of logarithms. So if this is positive, so it goes in the numerator. This is negative here, so it goes in the denominator. So what you get is that. And now we want to rewrite this as an algebraic expression. So this is one of these logarithmic. So what we do is we have to use the same base. The base for the natural log is e. So e to the natural log of x plus 1 divided by x minus 2 is equal to e to the 7th power. Ooh, that's a big number. Let's change that. Let's try 3. Okay, 3 cubed, or e cubed. So we get e cubed. So e to the natural log of that is just the expression. And e cubed, plug that in your calculator. E to the 3rd power is 20.08. Okay. So what we do is x plus 1 equals 20.08 times x minus 2. And so you're going to get x plus 1 equals 20.8x minus 2 times 20.8 times 2, which is 40.2 approximately, 40.167. And if you subtract 1 from both sides, 1x from both sides, you get 19.08x. And if you add 40 to both sides, you get 41.17. So this comes over here, becomes positive. And you can divide by 19.08. So 41.17 divided by 19.08, you get 2.16. And we can go back to the original equation and see if it works. So the natural log of 2.16 plus 1 minus the natural log of 2.16 minus 2 equals 3. It doesn't look right. Why is that? Why don't I think it looks right? Oh, maybe it does work. It might work. Yeah, let's try that. So the natural log of 3.16 minus the natural log of 0.16 equals 3. I kind of got lucky here because if this had been negative, then we wouldn't have had a solution. So we're going to do the natural log of 3.16 minus the natural log of 0.16, and I get 2.98, which is, so that's what it was supposed to be. I got 2.98, and that's just because I rounded off. You know, if this, I'm trying to think out which number would have changed, made it so it didn't work, but you know, I get an x value. I have to go back to my original expression and make sure that it's a valid number. So, you know, this has to be positive. X plus 1 has to be positive, which is true, 3.16, and x minus 2 has to be positive, which it just barely is, but it does work out. Okay. And finally, in terms of applications, I'm basically going to ask you to just be responsible for exponential growth or decay. So that is, you know, some population's a function of time is equal to some initial amount times e to the kt. And typically, there's two things I could give you. One is I could just ask you to evaluate this expression. You know, let's say it was say this is money in a banking account. And let's say I say there's initially $5,000. Well, the easiest thing would be to just tell you what the time is. But let's say the initial amount is 5,000, and the amount at some time later, t, is say $20,000. And I want to know how long to keep it in the account. And the k in this case is the interest rate. So let's say, you know, the interest rate is 6%. Well, use the decimal equivalent of 6%, so k is 0.06. So you have to solve for t in this case. So you'd have 5, you know, the amount that I'm trying to save, which is 20,000, is equal to the initial amount, 5,000, e to the k, which is 0.06 times t. So again, we don't do anything until we get rid of this constant. So if you divide both sides by 5,000, you'll get 20,000 divided by 5,000 is 4, and you get 4 is equal to 0.6 e to the 0.6t. And then you say, okay, exponential doesn't matter. I can use the natural log. I don't have to choose. In this case, because it is e to something, it still, you know, works, definitely works. But so what happens here is that the inverse properties of the logarithm and the well, in this case, that's true. But if it was some other base than e, it still would work. So let's just use that method. So you take the exponent and you multiply it by the original expression without the exponent. Well, the natural log of e is 1. So you get the natural log of 4 is equal to 0.06t, and then you divide both sides by 0.06 to solve for t. And, you know, bank accounts, you're talking about 10 to 20, 25 years, something like that. You know, that's the kind of numbers you're looking at. So I take the natural log of 4 and I divide by 0.06, and I get 23 years. Okay, so that's the easiest way. Is I'll give you some. I could give you the time, and you just have to evaluate this, or given k. In this case, I did give you k, but you had to solve this exponential equation for t. Now the other kind is kind of like, let's look at exponential decay, but the same kind of problem. I could give you the same problem in exponential growth. Growth is going to be some value, p of t equals p0 e to the kt, where k is greater than 0. And decay is p of t equals p0 e to the minus kt, where k is still greater than 0. So you could do that where k is still greater than 0, but the argument's going to be negative. This is when you have a negative sign here, it's a y-axis transformation. So this is exponential growth. Exponential decay looks like that. And typically we're looking at this part of the curve where it starts at some value and then it drops off. We usually don't worry about that part of the curve. Okay, so let me just give you an idea here. Let's say I'm going to give you some initial amount, and again, you need to understand the process here, because I'm not going to give you exactly the same problem. Otherwise, you're just copying stuff down. So let's say the initial amount, P of 0, is 4 grams of something. And let's say the amount at t equals 5, whatever that unit of time is. So P of 5 is equal to 2 grams. So there's two things that, what is K to make that happen, and what is the amount at some other time. So let's say I've done 0, 5, let's predict 7. So that's the kind of thing that I would ask. So let's look at the equation here, see what we can do. So typically, I'm going to assume it's growth, but it's actually decay. But what will happen is K will come out negative. So it doesn't really matter. You can pick either way. The appropriate K will happen. So first thing you kind of need to know is, what is P0? And typically your P0 is when time equals 0. Now there's cases where that doesn't happen, but under those conditions, this P0 is equal, P0 is P of 0. So that's 4. So I can add one little bit to my equation here. It'll be P of t equals 4 grams times e to the kt. So what I need to do now is figure out what is K. So what you do is you take the amount to, let's write it out here. So P of 5, so the amount of P of 5 is equal to 4 grams. I'll leave the grams off. E to the K, but this 5 is T, so you put 5 up there. But I've given you what P of 5 is. It's 2, so I put in that number. So I use this number as the T value and this number as the left-hand side of the equation. So now what I need to do is just solve this exponential equation for K. All I've done here is switched K and 5, so it's 5K. So if I divide both sides by 4, I'll get this. And I need to do that so that I can, get a coefficient of 1 in front of the exponential. Then I take the natural log of both sides. Again, because you can do that because it's an exponential equation. It doesn't have to be the base of e for this to work. So you take the natural log of e to the 5k, but I can take the exponent out, 5k, and multiply by the natural log of e. Let's go ahead and calculate the natural log of 0.5, which is negative 0.69 0.93. The natural log of e is 1. So I can solve for k. K is equal to negative 0.693 divided by 5. So divide that by 5, I get negative 0.139. So my equation now, P of t, is my initial amount, which is 4, e to the k, which is negative. So you can see that it correctly specified this as negative, which means it's decaying. And that makes sense because it's the value at some later time is less than the initial amount. That's what decay means. You're getting less of it. Okay, so that's now your equation. So if I want to evaluate the function as 7, it's just a matter of plugging in 7 into my equation and then using my calculator. And you know, after 5 years it was 2, so after 7 years it should be less than 2. So if you get something that doesn't make sense, you should realize it. Okay, so we have 4 times e to the negative 0.139 times 7, and you get 1.5, which is less than 2, which is less than 4. So this was at t equals 0, this was at t equals 5, this is t equals 7. So you can see how it's getting less and less and less and less. It's decaying. Okay, so that's it. Yeah, it's a long video, but I've gone into a lot of detail on all the problems. But again, if you're still listening, you know, don't just think because you've written this stuff down that you can read your notes and understand what's going on. If you don't understand what I did, or if you don't understand it well, you don't think you can generalize it to problems that may be slightly different, then you need to go back and look at your homework assignments, read the book, come and see me, come to go see a tutor, whatever. Okay, that's it.